Hi, and welcome to our talk on voice privacy challenge. My name is Jixun Yao. I'm a PhD student, and my co-author is Qing Wang, Zhang, PC Guo, Liang, Yuhao, and Xie. We all from the Audio Speech and Language Processing Group in Northwestern Polytechnic University. Today's content will contain 4 aspects. The first one is an introduction and what we proposed to do anonymized speech, followed by evaluations and results, and followed by conclusions. So first is an introduction. Speech data on the internet are proliferating because of the emergency of telecommunication, voice pay, and visual assistance. Such applications record personal data to centralize the service and easily be stolen by attacker. However, speech data contain rich personal sensitive information that can be disclosed by automated systems, such as age, gender, health state, and other sensitive attributes. And how to protect personal speech data? There are 2 general solutions. First is cryptography, and second is anonymization. Cryptography may sometimes be hacked, so it is not a suitable solution for protecting our personal speech data. Speaker anonymization is an effective technology to protect personal privacy that is becoming increasingly critical in light of the exponential growth of voice data. This technology is given to us by Voice Privacy Challenge, which also provides matrix benchmarks and evaluation datasets. Further to this, it also gives us a baseline system which we build on with our system and improve. So our work began with an analysis of anonymized speaker embedding from the baseline system. And this was the anonymized embedding is averaged by the candidate speaker vectors. The robustness of the ASV model determines the accuracy of anonymized speaker embedding. Furthermore, the baseline system also needs an X-vector pool, which adds the complexity of anonymization computation. Based on this analysis, we use lookup table for speakers in training sets as a speaker pool. And our system does not involve additional ASV models and X-vector pools. As for speaker embedding, we reverse a pseudo speaker embedding in lookup table to generate a pseudo speaker embedding and average the random selected speaker embedding in lookup table. Finally, the anonymized embedding is the weighted concatenation of averaged embedding and pseudo speaker embedding. In this way, our anonymized system also reduces the risk of insufficient generation of ASV model and the complexity of anonymized computation. Compared with the baseline system, our system has been improved as follows. First, we use an improved in and VNet tools to extract fundamental frequency and bottleneck features. And then we replace the X-vector extractor in baseline system with lookup table and speaker encoder. As for anonymization, we combine 2 types of speaker embedding to generate the anonymized speaker embedding. Finally, we use the CBHG-AR and our modified Haifa as the acoustic model and vocoder. Our work focused on the anonymization model. So next, I will introduce our proposed anonymization method. In this part, I will briefly introduce the framework of our proposed anonymization system, which is present in figure. The anonymization system consists of 4 models: feature extraction, acoustic model, anonymization model, and vocoder. Anonymization process in 3 steps. So first is to extract fundamental frequency, bottleneck features, and speaker ID. And then the speaker encoder is used as an anonymized embedding generator to generate the averaged speaker embedding and pseudo speaker embedding. That is, the average speaker embedding is a condition for pseudo speaker embedding that generates as output of the anonymized embedding. And the acoustic model predicts a mere spectrogram. Finally, vocoder reconstruct a mere spectrogram to anonymize the speech. As for our anonymization strategy, we combine 2 types of embedding to generate a final anonymized speaker embedding. First is average embedding, which is average the random select key speaker embeddings in lookup table. We generate the lookup table using Libre TTS 150 500 dataset, which contains 14 and 7 real speakers and 1 pseudo speakers. The speaker embedding is generated from the original speaker ID during training. In our strategy, the average embedding is similar to the mean X vector of a set of random select X vector from an X vector pool, but we do not need an X vector pool, and the lookup table is equal to our X vector pool. Second is pseudo speaker embedding, which is generated by pseudo speaker ID. The pseudo speaker does not correspond to any of real speakers in training data. This means that the pseudo speaker ID is not involved in optimizing the training process. And the real speaker ID and the pseudo speaker ID produce different distribution of speaker embedding during inference. Finally, the average speaker embedding and the pseudo speaker embedding weighted concat to generate anonymized embedding as output. So this brings us to our voice privacy challenge results. The first is evaluations. Our proposed system follows the voice privacy challenge data configuration, and the final results are evaluated by Libre speech test, Qing, and VSTK test datasets. And for primary equal rate results, our approach leads to a notable increase in average EER of up to 18.34% compared with baseline 1A and 29.7% compared with baseline B. And the highlight thing is different genders perform similar in our approach as compared with significant differences in baseline systems. We think this mainly because the X vector extractor in baseline system has better performance on men than women. But our system does not involve additional X vector models, so the ER result shown in our results perform similar in different gender. Moving on to our whatever rate results. The lowest WER is 3.84% on Libre speech test and 7.81% on VCTK in condition 3. And the absolute WER reduction is 2.47% over baseline 1.8 and 1.74% over baseline 1.B. We match all the 4 ER conditions with WER substantially lower than baseline. We believe that the advantage of our system is the use of lookup table instead of X vector extractor, and avoiding the mismatch due to robustness. We proposed an ASV model-free anonymization strategy, and our system uses average embedding as the condition for pseudo-speaker embedding to produce the final anonymized embedding. Under the voice privacy challenge evaluation plan, our anonymization strategy can meet all conditions by adjusting the weight hyperparameters and word error rate substantially lower than baseline system. Thank you very much for your listening.